All right, today is photovoltaic day, but before we get into that, I have a question for you all. I thought that Carmen was going to automatically grade the quizzes, but somebody said they couldn't see their quiz grade for quiz one.
Yeah, I can't see mine.
So then I went in yesterday and I checked the grade these quizzes box, and then it showed me all the scores in bold instead of regular. And then I got another email today, we can't see our grades. So I don't know what's up with that. So I went in again this morning, I checked that box again. We'll see, let me know if you can't see your grades. But somebody said they could see their grades for quiz 2 as soon as they completed the quiz.
Yeah, that's what happened to me.
I cannot for the life of me figure out why. So if on future quizzes, if you don't see your grade right away, please let me know and I'll click things at random until you can. What else do I need to tell you? Homework 3 has been posted. The due date was next Wednesday, but that's too soon. So we're going to move that one out a little bit, maybe the following week. Well, for sure the following week, but I don't know whether it'll be Monday or Wednesday. Okay, so let's see. I got to press a button here. 7. No, I don't want to place a call. Home, let's try that. No. This system is not fully debugged. Preset 7. Phew. All right. So at the end of last class, or somewhere during last class, we mentioned that OSU had agreed to buy a bunch of energy from Blue Creek Wind Farm, which is being built up in northwestern Ohio. And the question came up, are we actually using the energy directly from that wind farm? And one of our students, Spencer, who's not here, said he knows somebody who somehow, I don't know who it is, somehow somebody is involved with this process. And he got this quote from the guy via email. He said, I can't remember the exact figures, but he believes it's 1 per 2 cents per kilowatt hour less than what implied is the regular price, I don't know. He says, we're buying renewable energy credits and the energy, though it's not exactly piped directly to us. It's hitting the grid, and we're taking it from the grid at the same time. So you may remember that the first day of class, I mentioned that when you turn on the light switch or plug in your toaster or whatever to use energy, somebody at a coal plant somewhere is turning up the turbine because you need that energy right now, and they crank up that energy and it goes into the grid. I don't know if I talked about the grid. We're going to have Professor Costin come and talk about the grid, I hope. Anyway, so there's energy going on into the grid as people need it, and they're stoking up and calming things down depending on the demand. And then we also take energy from the grid. So if they're putting the energy in the grid up in northwestern Ohio, that energy is being spread out over Ohio, and whoever uses it, we don't know who uses it. It couldn't be determined. So we're just taking energy from the grid at the same rate it's being put in up there. So this raises the question, what is a renewable energy credit? So let's say Bob owns a wind turbine farm. And by the way, I used to say windmills, and somebody in the business slapped my wrist and said wind turbines. So I guess a windmill grinds grain. Ooh, that's good to know. And a wind turbine generates energy. So let's say Bob generates 1 megawatt hour in green electricity. The Blue Creek farm is going to generate 50 megawatts. In fact, we're going to be buying all of its capacity. So he generates 1 megawatt hour of green electricity. He puts it into the grid. And once it's in the grid, we can't distinguish those electrons from electrons produced by a coal plant or a solar plant or anything else. They're just electrons. And we can't tell who uses those electrons. OSU, at the same time, takes energy from the grid down here in Columbus. So the energy that we take is not the same energy he puts in. So the renewable energy credit works like this. Ohio State buys a 1 megawatt hour certificate from Bob. Bob makes money on the certificate, but remember, he also sold the energy to the grid. So he put energy into the grid, he got money, and then he sold us this certificate, and he gets money for that. That helps to subsidize his investment in putting up the wind turbines and so forth. And OSU owns this credit, and we get to say, look, we're in charge of, or we're responsible for 1 megawatt hour, and we bought 50 of these, 1 megawatt hour of green electricity. So we help subsidize Bob. Now notice that oil and gas are already subsidized by the government. So this is a way to make wind energy a little bit more competitive to help get it established. So then what OSU can say is we effectively, the 1 megawatt hour that we bought was supplied by Bob. It's not the same megawatt hour, but for every megawatt hour that we buy from Bob, that's a megawatt hour that doesn't have to be generated in Muskingum County by shoveling coal into a furnace. So that's how that works. Okay, so last class we discussed wind energy, and we saw that Northwest Ohio is pretty good for us, and Lake Erie looks very promising, somebody pointed out. Excellent. We also looked at planes. We found out that plane travel is expensive energy-wise. In fact, transportation in general is energy intensive, and so far we've looked at transporting us to visit Grandma, but we haven't looked at shipping, which is significant, so we'll be looking at that later in the course. And we also looked at solar thermal energy, which is heating water or air to get heat energy. Remember that heat is not the best quality energy. It's good for heating, right? But it's not so good for driving your car. And the next thing we're going to talk about is photovoltaic or PV. So what exactly is photovoltaic? A photovoltaic device is a device that produces a voltage or electricity when light shines on it. It's almost always silicon. The theoretical efficiency for silicon is 29%. The maximum achieved so far is 24%, and that's in a lab somewhere. That is not on a commercial scale. There are other materials besides silicon that can be used for solar energy, but right now they're far more expensive. I have some silicon cells here. I need to turn on these lights here. Hello, distance people. I'm trying to figure out how to work the lights. That wasn't it. That's a little better. That has no effect. So, first of all, I have here this solar panel that the distance guys can't see. Wait, I have a list here. Which preset will show them that? Center of blackboard, 5. 5, I say. 5. Oh. 5 displayed on here. Maybe if I press preset and 5. Oh no! Oh, I hate this system. Is there a clear button? No. Is there a home button? Yes, but I don't know what it does. Oh, I was afraid of that. That's what I don't want to do.
Do that preset thing again. It said to select.
Did it? Did it? Preset. 5. I'm afraid it's going to set them.
Boom.
Yay. You distance guys still can't see this. Gee, that's too bad. Well, this is where it's good to be in class. Maybe I'll bring this up. This is a solar panel from a satellite here. I'm looking at the screen there. I'm just trying to catch the light off so they can see it's shiny. This was built by, I think it was Rockwell. I forget. And it doesn't have the power on here. Rockwell control number, serial number, part name, outboard solar panel, manufacturer name TRW. So it was made by TRW, which is now part of Northrop Grumman. This one was for a satellite, and you may wonder, well, what's it doing on Earth? And the answer is that it was a spare. In case something went wrong with the launch, they had a backup solar panel. My good fortune is nothing went wrong with the launch, and so they had this leftover solar panel, so they said, let's give it to a university. So I use it for show and tell. I invite any of you to come up here and try to lift it. You could be the one.
Spencer.
You want to do it?
Spencer, you got it.
All right, let's give it a try. Holy cow. Yeah,
Yeah,
it's just like,
it's unbelievably light. Why is that?
there's nothing to it.
Well,
aluminum?
what's our motivation for making it light?
Because you got to shoot it up into the space.
Space. That's exactly right. Anyone else? Come on.
So is
be
it
brave.
like aluminum carbon fiber, or what is it?
Darned if I know.
I
I
know
see
that
some
the-
aluminum on the side here, so it may be aluminum honeycomb structure. Any other of you guys want to give it a shot? Okay. Too bad there's a $200,000 solar panel back in the 1980s. But the technology hasn't really changed that much. And I invite you guys to come up after class and take a close look at this. stuff. You distance guys, I'm so sorry you don't get to see that. Oh wait, look! She brought in an instrument too. Oh, this is promising. Here is my favorite instrument in the world. The curve tracer. And I'm gonna let it warm up for a sec while I get out my wires. Somebody cleaned up the lab last night. I got this all set, and then I looked in this morning. I said, "Oh, somebody moved the wires." They were trying to be neat. Oh. See, black to black, red to red, something like that. Let me use the document camera. Let's put this on the, I forget which is which, document camera. And let me see if I can figure out how to turn this on. Power. I have one solar cell on here. Right screen, close-up of left screen. That would be 6. This is a polycrystalline solar cell. I'm allowed to carry it around because it's already broken. It's very thin here, and I don't know if you hear that sound. It's very gentle. And if you hold it up to the light, you see all these different blue patches. So that's how we know it's polycrystalline, just by looking at it. I'll pass this around, but it's sharp. And if you break it, you're a dead man. Not really. And then here's what I'm going to hook up to the curve tracer. Here is a array of 3 solar cells, and they have a little plastic lens array on top. So that's what these bumps are. Now, you may say, what happened here? Why is there only 3 instead of 4? Here's my motto. Never let students touch your stuff. So I have a solar simulator in the lab, and a student took this thing and said, well, what happens if I bring it really close to the sun? And the solar simulator is actually an overhead projector bulb. Remember those? It's really hot, and he melted it. That's why I only have 3, but I'm not bitter. So what I'm going to do is I'm going to hook this puppy up to the curve tracer. But before I do that, I have to go back to close-up of center of blackboard 5. And left projector will go back to the computer. And those guys can exactly not see the curve tracer. Oh, you might be able to see. You can just see it. It's down here. Oh, I hope so. So I'm going to make the connections. Hey, look, one of these wires is red. I think I'll connect that to this red wire. And I'll connect this to this black wire. And what this thing does is it plots. It's going to sweep the voltage, so the voltage will be on the horizontal axis, and the current will be on the vertical axis. Now, solar cells are always diodes. That means that they conduct current for positive voltage, but not for negative voltage. So let's see if this looks like that. I'm turning on the voltage. Oh, I forgot to flip this switch over here. Here we go. Whoa, look at that. Can you distance guys see that? Yes, they can. So when let me try illuminating the scale. As soon as I find the scale illumination button will be golden. Graticula. Does that help at all? Doesn't help those guys. Does it help you guys?
That's good.
Okay. So, and I can change the horizontal scale. When the voltage is positive, there's some voltage before it turns on, and then current can flow. If the voltage is negative, there's no current. Okay, there's a little bit of leakage current. Shh, we pretend not to notice. Now, let me just check one more thing here. I gotta move this dot so it's right on the 0. So I know that that's 0 current and 0 voltage. All right. If someone told you, as I'm about to, that the power dissipated in a device is equal to I, which is current, times V, which is voltage. I is current, nobody knows why. And in this quadrant, the voltage is positive and the current is positive, so the power dissipated is positive or negative, take your pick. Positive, right. And in this region, the voltage is negative and the current is either 0 or very small, but it's negative. So the power dissipated is a negative number times a negative number will give a positive number. So this thing is dissipating energy just like it's supposed to. Now I need a light source. I just learned yesterday that this thing is now a flashlight. I love technology. This is why everyone should be an electrical engineer. As soon as I find the right button, I found a button here that says light. Ooh, there's a little light coming out. Let's see what happens if I shine light on the, which one did I connect here? This guy. Oops, I can't see the screen. I can see the screen. All right, so when I shine the light on here, you can see that in this quadrant, the voltage is positive, but the current is negative. So this thing is dissipating, negative or positive?
Negative.
Negative, so if it's dissipating negative power, it's producing power. And that's how solar cells work. So there, it's just a normal device with light on it. As long as I operate in this quadrant, which I can't get this thing to go there, in this quadrant, then I'm producing power, and that's how solar cells work. You can imagine that the farther down this goes and the farther over this goes, the more power there is. So the voltage here that it turns on, it depends on what material it's made out of. For silicon, it's always going to be around 0.7 volts, something like that. For you circuits guys, that's a familiar number. Other materials, you might have a different voltage, okay? And then how much current you get depends on how you structure your device and how efficient it is. So I like to show that because it's so much fun. And the curve tracer is the best instrument ever invented. Those of you who are in the class, if you want to come up and play with that later, you can. All right, so now I'm going to go back to preset 7 and resume our lecture. So photovoltaic means it produces a voltage. Again, silicon, the best you could ever hope for is 29%. And that's if you had a perfect device with no defects in a lab and it's clean and the sun is shining and you know your horoscope is in line. What limits the efficiency? Well, for one thing, silicon is transparent to infrared. Here is a plot of the wavelength of light coming from the sun. This upper curve is in space, and this lower curve is after it's gone through the atmosphere, which sadly is where we are. If you were the satellite guys, you would get to use this, but we're not. So, band gap of silicon corresponds to 1100 nanometers. So all of this energy over here, we can't collect it because the solar cell is transparent to it. Let's see. Ultraviolet and blue light are absorbed too close to the surface of the chip. So the light gets absorbed, the light hits the chip where it is, and it penetrates some distance, but then you have to collect the electrons. We have classes you can take, but the electrons have to be collected near a junction, and the junction is not at the surface, and it cannot be at the surface, and therefore, well, actually you can plan where it is to get the most absorption, but those high energy photons are absorbed so close to the surface we can't collect the electrons. So we don't get much energy out of those. So we can only collect the ones that are absorbed deeper into the cell. We actually put that junction at the best depth to try to collect the most electrons, but we can't get them all. Also, it turns out that light is a particle on Mondays, Wednesdays, and Fridays, and alternate Sundays, and it's a wave on Tuesdays, Thursdays, and Saturdays, and the other Sundays, except south of the equator, where it's the opposite because of the Coriolis effect. So today, light is a particle, and for every photon that I receive, I can generate optimally 1 electron. Okay? So it turns out that remember, this is where the silicon is transparent. This is red here, infrared and red, and these turn out to be low energy photons. Fine. These are high energy photons up here, blue and green, these things. They're high energy photons, but can I get more electricity out of them because they're higher energy? No, because there's still the same number of photons, and I only get 1 electron per photon. So even though there's a lot of energy in this part of the spectrum, I don't get more energy from it because it's green or blue or anything like that. So the rest of the photon's energy is wasted. All I get to collect is that amount of this energy. This is plot of energy in electron volts. Here's 1.12. This is the band gap of silicon. This looks like 2, 3. So these photons in the 2 to 3 electron volt range, I still only get 1 electron. Okay, so the rest of the energy that they have is given off as heat, which is also a nuisance. So those two things together lead to the 29%, the fact that we lose the infrared and that we only get 1 electron per photon. But that's in an ideal world. There's other losses, like light's reflected off the surface. Where's that wafer? Is that around? You believe it. I'm showing it to the distance guys. This is shiny, right? Shiny. Can you see that? No, we cannot see that. Well, it is. And so we lose some light there. Now there are coatings we can put on to reduce the reflectivity. And the more layers the coating has, the better you can reduce the reflectivity, but the more expensive the cell gets. Trade-off. Electrodes on the surface. So, let me put this on the document camera again. Well, I don't know, maybe you can see it just here. This one, yeah, you can see it looks like this one. So there's contacts here, and then there's other contacts here to collect the electrons. The closer together the contacts are, the more electrons you can collect. The closer together the contacts are, the more you block the light. That's another problem. Okay, can't space them too far, we lose the electrons, and if they're too thin, so you can make them thin so they're more transparent, but then they become resistive and you have losses there. Pesky laws of physics are always busting my chops. Furthermore, the 29% is for monocrystalline silicon. That's what this highly expensive solar panel is. This highly not expensive X solar cell is polycrystalline, that's cheaper. So it's cheaper, but it's not as efficient. So which one are you going to paper all of Arizona with? It's hard to say. You know, we could get a lot more energy if we had those, but these are cheaper. There's losses at the borders of these crystalline domains. We have classes you can take. So photovoltaic means we're converting light to electricity. So let's talk about solar photovoltaic, and this will be personal photovoltaic as opposed to a farm, which we'll talk about later. So if I put solar panels on my roof, I can do the same calculation we did for solar thermal, because I know how big the roof is, and I know how much sunshine we get, blah, blah, blah. But the problem is, we said the solar thermal was 50% efficient, and we were being generous. Here, we could say 20% efficient. I say we're still being generous. You're not going to get 20% in anything of reasonable cost. Maybe 10% is more realistic. But we could pop out the same calculation and figure out how much energy we could get. Photovoltaic, the UK, so this is McKay's numbers. He covers his south-facing roof, because he read the journals and articles and also put it on the south side. And he has 10 square meters per person of roof area. He's going to say, let's be generous and pick 20%. I don't think he can afford it. Then let's assume he's got the 110 watts per square meter insulation that Cambridge gets, and he comes up with 5 kilowatt hours per day, per person. The per person's not on there. We get 140 watts per square meter. Remember, we get a little bit better sunshine, so our result is more like 6 kilowatt hours per day. But of course, I can't put photovoltaics and solar thermals on the same roof. So these numbers are optimistic. I just remembered something else that curve tracers use. They dispense Coke. So we're measuring solar energy at the point of use. But it takes energy to make a solar panel. And it takes energy to transport the solar panel into Afghanistan. So there's something called the energy yield ratio. That's the energy delivered by a system during its lifetime, multiplied by the energy required to make the system. So when you do these calculations, then you have to say, well, how long is this solar panel going to last? Or when do I need to break even? Is it going to last for 20 years, or is it going to last for 10 years? Or am I going to run it until it drops, or a pigeon's going to poop on it? Also note that photovoltaics, so this is another problem, they produce DC. So direct current. That means that it's like a battery in a sense, because it's DC. It's not a battery, it doesn't store energy. But all of our transmission lines are AC, our outlets are AC, all of our curve tracers and toaster ovens and all that stuff want to see AC. So when you put solar panels into the mix, you have added cost of circuitry to change the DC to AC. Those are called inverters. So it's just important to remember when you're considering the cost, it's not just the solar panel itself. You also need that inverter energy. And you may decide you need batteries because the sun's going to go behind a cloud. All right, back to our regular scheduled programming. So we looked at personal photovoltaics, and now let's look at what would happen if you had a photovoltaic farm. How much of Ohio would you want to cover with solar panels? How many people think 1%? Nobody's biting. How many people are comfortable with 5%
Sorry, to do what?
to cover with solar panels
Right. For what?
to produce energy?
Enough energy or just
That's the question. We're trading off how much energy do we need with how much land are we willing to give up for it. So that's kind of the question. For example, I don't want to cover half of Ohio with solar energy because I happen to know that half of Ohio is currently used for agriculture, and I like to eat food. So I'm not willing to go that far. I might be willing to go 5 or 10%, depending. But once you put a solar panel there, you can't put anything else like crops. Of course, we can put solar panels on tops of buildings if we can afford it. Here is a photovoltaic farm. This one is in Spain, I believe. That is a big honking farm. What is lucky about Spain?
Sunny.
Sunny, yeah. And it's fairly dry, so they don't have a lot of cloud cover, so they're closer to, I don't know if they're closer to the equator actually, but I know that they have a very sunny place, that's why people go there for a vacation. So that's a pretty big solar panel array. There's a building here, you can see that. That's pretty big. This one generates 20 megawatts. It gets sun 300 days a year because of they have less clouds. It's a better latitude than Ohio does it here. Powers 20,000 homes, whatever that means. You know, let's put that unit in idea in our favorite units with kilowatt hours per day per person. Okay, so here's a solar energy farm for the UK. So he's comfortable with 5% of the UK covered because he knows that they have to have sheep. He's going to say 10% efficient. They have 4,000 meters squared per person. Here's the 5% of the land. Here's their insulation at 110 watts per square meter. Here's the efficiency. And then this is all unit conversion, 50 kilowatt hours per day. Yes?
is the 10% counting for the DC to AC conversion and all that kind of stuff?
Yeah, he doesn't specify, but my guess is no. I think he's talking about direct power. So you're right, there will be additional losses in the circuitry.
Okay.
Excellent question. So I said, well, let's see how that would look in Ohio. 9,000 meters per square person, 5% of Ohio, is the most I could live with. 140, we have a little bit better sunshine, 0.10, and I came up with 150 kilowatt hours? Really? 3 times better? I better check my work. Well, first of all, we have more than twice as much area per person. So Ohio's not as densely populated as England. So that's one for us. And the other thing that we have going for us is we have a little bit better sun. So these two things combined actually make our solar farm potential 3 times better than England, which is significant. All right? So here's the stack for the UK so far. Car, jets, here's wind, solar heating, solar personal PV here. This is putting solar panels on your roof, and this is a solar farm, solar panel farm. This house has lots of photovoltaics. This is not my house, sadly. So if we live in the United States, we decided last class that we should put our farms in
Southwest.
Southwest. Looks good. How about Maine? No, I don't think so. All right. Here's one in Arizona, Agua Caliente in Yuma, Arizona. And you can see the PV panels here. And there's, I don't know what this is. I'm trying to get a sense of the scale, but I can't figure it out. This one produces 250 megawatts at noon in August on this particular day in 2012. When it's done, it's going to be close to 400 megawatts. It's already the largest in the world. It's not done yet. And this one is direct solar photovoltaic. So we haven't talked about this yet. This is take my PV panel or my satellite panel, stick it out in the sun, and the sunshine lands on it. But it is possible to concentrate the energy, and that's what these guys with the little lenses on them are doing. Let go. So this guy, I should pass this around. These have little lenses on them. That helps concentrate the solar energy. And by doing that, if the lens is this big, you can make the cell this big. So now you've reduced your cost. Okay, you had to add the lens, but that's cheaper than the silicon. So you can have smaller silicon. So we should look at the potential of concentrating solar power. We already did this. I have a couple duplicate slides in here. Oh no. So here's a kind of solar farm. There's a couple of kinds of solar concentrators. One would be to concentrate the light on a photovoltaic cell like you're holding there. This is yet another different kind, which is wacko. I don't know who proposed this. They must have taken a lot of drugs or something. And the book doesn't discuss this kind. But the idea here is there's a whole array of mirrors, and all of these, just mirrors. They're aimed such that when the sun is shining, the light hits the mirrors and it all gets focused on the top of that tower. And that produces a boatload of heat. And what that heat does, it actually melts salt. So they've got molten salt flowing through pipes. They come up here, they get heated up to a bazillion degrees. I think it's on the next slide. I think it's like 1100 Fahrenheit. A bazillion, we'll say. It's hot, right? And then they pump the hot salt, molten salt, to a generator, a boiler. They use it to generate steam, which drives a turbine, which creates electricity. In that case, the electricity is AC. And the salts are nice because, it says right here. The salts are nice because they aren't toxic or anything. Salts are available everywhere. This one over here is a parabolic reflector, and it focuses the light to this line. This line contains a pipe with either salts or water in it, and gets melted. Here's one at Crescent Dunes to be completed in 2013. This is in the southwest somewhere. This one has 20,000 heliostats. The heliostats are the mirrors, and they can be moved to track the sun and keep aiming the sun at the tower. I was close to 1,000 degrees Fahrenheit. And the nice thing about the salt is it holds the heat for a long time. So one of the big problems, again, with our energy supply from coal is that we can't store it. So when I turn on a toaster, they have to generate more electricity down in Muskingum County. These guys, the salt holds the heat for a long time. So even after the sun goes down, there's still a lot of latent heat in that molten salt. And they're saying they can still use that to drive those generators during the night and continue to produce energy. So in a sense, that's a storage of energy. It's not a battery, it's storing in its thermal form. So they said they could get it for 12 hours after sunset. I think that's nuts, but I haven't done the calculations.
Also beneficial because the whole system, it's essentially a coal plant, but instead of the coal being the heat source, it's the sun being the heat source.
Right, you're not burning anything.
Right, so if you did run out of sun and heat, you could essentially have like some sort of oil or coal to even.
Yeah, hypothetically you could burn coal and drive those same turbines. Yeah, my guess is that they're not built that way because there's no coal burner, fireplace, but still, yeah, in principle. So here's another picture of how it works. The heliostat, helio for sun, and stat for, I don't know, what? Stay the same, but it doesn't because it moves to track the sun. Here's the receiver. The molten salt gets pumped through here. There's a cold salt tank. This one gets pumped to the hot tank. Hot tank goes in here, drives the steam generator. Steam makes steam, drives this turbine, and we're going to talk about a turbine in a little bit. There's some lost heat here that gets I don't know what that happens. And then the cold salt goes back here. It's still molten because they got to pump it up here. But anyways, basically that's how it works. But the only reason it works is because they can concentrate a boatload of sun energy on one point. So if you've ever gotten out a magnifying glass, and it's the same kind of principle. Here's another one in Spain. This is the world's first commercial concentrating solar power. Then near Andalusia, it's 11 megawatts. I just love these pictures. I never get tired of showing them. Some pros and cons. The turbines are costly, but you know what? Turbines are costly in a coal plant too. Using heat to generate electricity, we've also talked about this. It's not that efficient. That's one of the reasons that coal plants aren't more efficient, because they're only 40% at best. But this kind of solar energy is cheaper than photovoltaics. All salts are common and non-toxic, doesn't harm the environment, so these are all good things. Here's a linear concentrator. So here's a parabolic reflector, focuses the energy on this pipe, and molten salts or sometimes water goes through that pipe. The pipe is probably black to absorb the heat as much as possible. Whatever the hot fluid is, it goes somewhere, it boils water, creates steam, drives a turbine. This is the Archimedes solar farm in Italy, and this one uses molten salt technology and produces 5 megawatts. And there are rows and rows of these things, but you can only see one row in this picture. Why is it a parabola? If you go back to high school geometry, something about parallel lines entering a parabola always focused to a point. So the parabola's curvature is constantly changing. So depending on where the rays hit, the curvature is such that the bisector, the angle of the normal, blah, 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 directs all the rays to the focus. So if you have a linearly parabolic trough, all the light that comes in is going to get focused to that pipe, which is coming out here. That's why it's a parabola. Whoa, here's another linear parabolic solar concentrator that Areva is working on with Sandia National Labs. The only thing is I don't see the parabola, do you? I see the pipes. So what's this business? Is this supposed to be some kind of parabola? Sure doesn't look like it. Well, it turns out that that is a Fresnel lens. So a Fresnel lens is think of a big thick lens and you chop it up into sections because all you need for the lens is the back surface and the front surface curvature. So usually it's easier to just make it this way, but if you chop it up, this section here is a curvature of this section here is a curvature of this section, and now you've flattened it. Why would you want to do that? Let's say you were making a lens for a lighthouse. If you made the lens as thick as it would need to be, it would be this thick. That's a lot of glass to haul up those stairs. So this saves a lot of material. You guys are probably too young. We used to have these devices called overhead projectors, and there would be a Fresnel lens on that flat bed, and it would project the image up here. And if you took it out, you could see the rings. This is a picture of an actual lighthouse. They're famous for these Fresnel lenses. You can see the edges of the lenses there. So what they did in this previous guy was they flattened that parabolic trough. I don't think it saves any material because it was a mirror, so you didn't need the backside, parabolic mirror, but I think it may have made it easier to mount because they didn't have to support that parabola in case it rained or there were winds or something. But I don't really know, I'm making that up. You'll often find that to be the case. You could concentrate light onto photovoltaics too. Silicon turns out to be more efficient at higher light concentrations. So if I were measuring the curve on this curve tracer and I increase the light, I would actually measure a higher efficiency. So that's a plus. Also, the chips can be smaller. We said that before. If the lens is this big, it's collecting all the light in this area and focusing it to this area, I've just saved a lot of material. And silicon's cheap, but solar cells are not. But I also have to keep the cell cool because you don't want it to overheat, so you need to have heat sinks, so there's a lot of material involved there, but it's just metal, not solar photovoltaic material. Here's another style of parabolic. So instead of being a linear parabolic, this is a parabolic dish. You've seen parabolic antennas probably at the airport and stuff like that. Same principle except different wavelength. So here, there's actually a Stirling engine. It creates electricity from heat up there aimed at the focus. Here's one that Rhea, our TA, found a picture of. I could not find out where this was or if it's even real or just someone's imagination, but it looks like they put a parabolic dish on the side of a building. Here is an array of concentrating solar dishes. Now, you could put a solar cell at that concentrator, but these all have thermal conversion. So there's 3 basic styles then. There's flat photovoltaic, put it out in the sun. There's concentrating dishes like this, and then there's linear concentrators like that. So here's a quiz. Which one do you think is which? Which do you think this is? Flat solar thermal or solar photovoltaic? Do you think it's a concentrator? I'm all ears.
Photovoltaic.
We have one guess that says it's photovoltaic.
Yeah.
Okay?
Okay.
Could be. I know it's not a concentrator like this with a tower because I can't see the tower. So I know it's something else. It looks like long linear arrays, so it might be a linear focusing one, but I can't see closely enough to see if there's pipes running down the middle of those, because it could be rows of photovoltaics like this. This is definitely photovoltaic panels, because they're blue, and they look like just flat photovoltaics, and I don't see a tower there. Plus, we're all aimed in the same direction at the sun. These guys, this is clearly a focusing, concentrating unit. I see the tower, and I see that array of mirrors all facing it. So you can tell by looking at the pictures at least somewhat. All right, so I've been keeping track of these numbers, and here is McKay's numbers for England, and I squished them down to make this stack the same as this stack. Our plane and cars were roughly the same. At least we said they probably were. I've been trying to find better numbers for plane travel for the average American, but those numbers are really hard to find. So for now, I'm just leaving it with his estimate. And here's their wind. Ours was not quite as good. Here's their solar thermal, I think that says. Here's our solar thermal personal. Here, we thought we could get more, and part of that was we had more area per person and we had mostly more sun. Here's their personal photovoltaic. Here's our personal photovoltaic. Here's their PV farm, and ours was 3 times that big. So we're actually starting to look a little better. Of course, we haven't finished our consumption stack. My guess is we consume more, but we'll see.
What was the percentage again that we were covering in Ohio?
5%.
5%.
That was based on a 5% estimate. So here's another form of solar energy. What about biomass? So biomass says, let's let plants do the conversion. So sun shines on plants. Plants use photosynthesis, create sugars and starches and things that have energy in them. And then we burn that, or eat it, or feed it to an animal and have the animal do work for us. Here are the power densities in watts per square meter of the crop for various materials, which you can't read from there. So this one's wood, this one's rapeseed. This is converting rapeseed to biodiesel. You may hear a little bit about that, so there's some efficiency lost there. Maize, that's British for corn. Sugar beet, you don't speak English over there. Short rotation coppice, calorific value. I have no idea what coppice is. Some English thing. Here's a short rotation coppice, calorific value. This is energy crops, calorific value. I don't know what that means.
Why is there 2 lines there?
The 2 lines, I
on those.
don't remember.
Okay.
This is from our book. Does anyone remember? I should put it on a quiz, then we'll all remember it. I don't remember. Sorry, I don't know. Miscanthus to electricity. What's miscanthus? Grass. So this is one that's being looked at in the United States quite a bit. People are saying, well, maybe switchgrass. Maybe we can get, actually switchgrass is down here. It's a different kind of grass. So here's the energy content of switchgrass. Here's corn to ethanol. People are talking about doing that there. We've been subsidizing corn farmers to grow corn so we can turn it into ethanol and put it in our cars and drive around. Wheat to ethanol. I'll be darned. Jatropha, I don't know what that is. I don't know why these are brown. Sugarcane. Brazil, this says Brazil and Zambia. Brazil produces a boatload of sugarcane. If you go there, you'll see them burning off the fields once a year so they can get the sugarcane, and they actually use it to produce alcohol, and their cars all have, they burn gasohol that's got a lot of alcohol in it, because for them it's really cheap to do this. They don't have much, well, they didn't have much oil reserves, and now they've found some more. This is tropical plantations, eucalyptus, and this is tropical plantations with an asterisk that didn't get captured on the slide, but it's in the book and I don't know what it means. So McKay went through and he figured, well, if we cover so much of the UK with these kinds of crops, and we take into account we're growing food, biofuel, wood, waste incineration, and even capturing landfill gases, which he counts as a biomass. You figure 24-hour kilowatt hours per day per person is the best they can hope for. It's pretty optimistic. So here's how it works. You can grow high energy crops. You can grow them specifically to burn in a coal plant or a substitute plant, so that'd be a substitute for coal. Or you can grow things that you can turn into a ethanol, and that would be a substitute for oil. Now some people say it takes more energy to grow corn than you can get out of it. They say if you take into account the energy used for the tractors to plant the corn, the energy used for fertilizers to make the fertilizer, the energy used to harvest the corn, the energy used to transport the corn seed to your farm in the first place, if you consider all those inputs, it takes more energy to grow the corn than you can get out of it. Does anyone have an opinion?
It's probably true.
It's probably
Tim
true.
McKay said that that's like a myth, that it was like slightly, like the energy lifetime thing was like a little bit over 1. I don't know.
For corn to ethanol?
Yeah.
Did he say that?
I'm trying to remember. I know it's like really, it's ridiculously small how much energy you get
Yeah.
out of it, but it was like just barely
breaking even.
breaking even.
So I looked into this, and I am not a scientist in this field, but from what I could read, I went to some of the technical journals, and as near as I could tell, if you take into account the energy to grow the corn, and you harvest the corn, and you burn the corn and turn it into ethanol, you almost break even, not quite. But if you collect the stover is a word I didn't know. That's the stubble that's on the crop after the field after they cut down the corn. If you also collect that and burn that, you come out ahead. So whoever's right, I think it's very close to a wash. It's not clear to me that this is a good use of our time. You can burn agricultural byproducts that are there anyways, like the stover. Or maybe you grew something else, and when you were done, you had this junk left on the field, you just burn it. That stuff wasn't grown for fuel because it was a great fuel, it was grown because you really needed soybeans or something. But at least it's there, you burn it. Now, it still creates CO2, but you can get energy out of it. And then you can grow food and eat it, or you can feed it to animals, like I say, and have them walk around and mill your grain or whatever. Biomass in the UK. This is a chart that's true for everybody. Start with the sun, shines on a plant. The plant converts the sunshine to something useful. It could be fuel. Maybe you can convert to electricity or food, and somehow or other we use it. So converting to electricity, there'd be steps in between here. Converted to a fuel that we burn to create electricity. So every step loses energy. The more conversion steps you have, the more efficiency losses you have. And the step 1 from the sun to the plant is already less than 1%. It's unbelievable how much energy is coming from the sun. And plants, which are pretty good at soaking that up, can only use 1%. And then you have other things that make it worse, these other steps, so we could assume a third of a percent of efficiency. And let's assume you can grow crops on 75% of the UK. It's a good thing he didn't put solar panels on all of it, because he needed some for this. 4,000 meters per square person, 75% of the land. Maybe he's growing stuff on top of buildings too, I don't know, blah, blah, blah. These various efficiencies. He ends up with 24 kilowatt hours per day. That's how he got that number. And remember, that includes the food that you eat. Biomass Ohio. Well, we currently use 50% of our land for agriculture. We also have twice as much land per person, and we have a little bit more sunshine. When I cranked out the numbers, I got 50 kilowatt hours per day per person for Ohio. This includes energy from food we eat, so that's important to keep in mind. I think it's important to eat food and stay alive. We'd have to grow fuel crops instead of whatever crops we grow now if we wanted to use that for electricity. So just making sure it's clear that the 50 kilowatt hours per day per person doesn't all go to drive our cars. And there are social issues relating to corn. Some say that corn uses more energy than it produces. We talked about that. The ethanol is made in distilleries. They're powered by electricity made from coal. Oh, dang. I hate that. Got to put fertilizers and pesticides. Those go into the environment. Require farm machinery to plant and harvest the corn. That uses oil, which has to be refined. So there's all these energy inputs. Requires water to grow corn, so they'll irrigate those fields. That has an impact on the environment. And then you have to transport the grain to the distillery so that you can make it into ethanol. So these are the kinds of energy inputs we were talking about before. The USDA says that if you use ethanol, you produce fewer greenhouse gases, about 20% less than if you use gasoline. Does this number take into account the petroleum we used in the last slide and the coal we used in the last slide? I don't know. So this is where, if I were going to present this data to you guys, I should go and do my homework and find out what's behind that number, where they pulled that from. So to summarize solar energy, location is everything. Personal solar helps, but it's small. Putting a solar panel on your house, either thermal or photovoltaic, helps a little. Solar farm is better, more efficient. Biomass, probably not the way to go. How's the UK doing so far? Looks pretty promising. So these are not on the same scale now. Here's the English one, and there's biomass up there. Wildly optimistic. Here's ours here, and to a different scale. So this is 50, and that's 24. But we're looking pretty good. Now we got to look at heating and cooling. And we may find that we have more consumption here than England. Well, we'll see. And we would start that, but there's only 5 minutes left to the class. So we're going to start in on heating and cooling at the next class. So for those of you who came in late, the homework 3 is posted. It says it's due next Wednesday, but it will be due later than that because we're just starting to get into some of the topics on it, so don't stress out. All right, are there any questions? Aces. See you next time with a brand new show.